Welcome to today's deep dive. We are so glad you're joining us. I want you to picture the smartphone sitting next to you right now. Like when you think about its design, your mind probably goes straight to the sleek glass, the curved edges.
Oh, absolutely. Or like the intuitive user interface.
Yeah.
People mostly think about the aesthetics and the end user experience.
Right. But here's the secret. While those aesthetic and functional design choices account for only 5 to 15% of that product's total cost, they actually dictate up to 70% of the product's delivery and supply chain costs.
Yeah, up to 70%. It's a massive number. It fundamentally changes how you view the physical world, honestly.
Totally. Which is exactly what we are focusing on today. Our mission for this deep dive is to explore Module 3, Section C, Product Design Influence. We really want to show you how getting a product's design right from the very start is, it's essentially the ultimate shortcut to supply chain efficiency.
Right, because it saves money, it reduces massive headaches down the line, and it still gives the customer exactly what they want.
Okay, let's unpack this. Because we are looking at product design not just as an art form, but basically as the DNA of the entire supply chain.
I love that analogy, the DNA. Because the decisions made on a drafting table, or in a CAD program these days, they create this huge ripple effect.
Oh, for sure.
It governs everything from the specific machinery you need on a factory floor to the exact number of boxes you can squeeze into a freight container.
But to really understand how design exerts that much control over the supply chain, we first have to look at, how things are traditionally designed and, frankly, why that old method is completely broken.
Right. The historical baseline, the traditional framework is what the industry calls the over-the-wall approach.
The over-the-wall approach. Okay, how does that work?
So it operated on this strictly sequential, highly siloed process. Like marketing would gather customer data, compile a list of features, and then just toss those requirements over a metaphorical wall to engineering.
Just throw it over the wall and say, good luck.
Exactly. And then engineering drafts this complex, beautiful schematic without consulting any of the downstream departments, and they throw it over the next wall to purchasing.
I have to push back on this method a bit because it sounds like a terrible corporate game of telephone.
That is exactly what it is.
It reminds me of software development before agile methodologies came along. You build this massive, complex architecture in a vacuum, and only after it's totally baked do you hand it to the testing team.
And they immediately find 50 critical bugs.
Right. And now those bugs are deeply embedded in the core code, so fixing them is a nightmare. This over-the-wall thing sounds like you're unknowingly baking manufacturing or shipping nightmares right into the product.
You absolutely are. So purchasing gets this design, and they realize half the components are wildly expensive or take 6 months to arrive, so they buy what they can, toss it over to production. Production gets it and realizes, oh, great, the tight tolerances mean we have to completely retool our assembly line.
Which costs a fortune, I imagine.
A massive capital expense. And then finally, they build the thing, hand it to logistics, and logistics looks at this weirdly shaped, incredibly fragile item and realizes they can only fit 20 on a pallet instead of 100.
Wow. Completely blowing up the freight budget.
Right. The cost to fix a design flaw on paper is practically zero. But once it hits the assembly line, the cost is astronomical.
Which is why there had to be a better way. And that brings us to the modern approach, right?
Yes. Collaborative design. The solution is simple. Eliminate the walls. Bring all the stakeholders to the table right at the conceptual stage.
So engineering, purchasing, logistics, everybody.
Everybody, including external suppliers and even key customers, all before a single prototype is even built. By doing this, you balance the vital attributes.
So you're balancing functionality with efficiency and quality and serviceability.
Exactly. If purchasing is in the room when engineering suggests a rare titanium, purchasing can immediately flag it. They can say, hey, that material triples the cost. And engineering can pivot to standard aluminum right then and there.
Here's where it gets really interesting, though. Because once we bring everyone to the table, what is the big picture goal? We aren't just designing for the end user anymore, are we?
Not at all.
Yeah.
You are designing for the physical journey the product has to take.
It's like playing a high-stakes game of Tetris with cargo.
That is the perfect way to describe design for logistics, or DFL. The main objective here is minimizing transportation and storage costs.
Yeah.
And the most critical tool within DFL is unitization or containerization.
Containerization, meaning designing the product to fit into a specific box.
Right. You are engineering the product's dimensions to perfectly align with standard box sizes. And those boxes have to pack flawlessly into master cartons, which then have to maximize the footprint of a standard shipping pallet.
Because shipping empty air is literally the fastest way to lose money.
You pay for the space, whether you use it or not.
Yeah.
And balancing that space requires navigating two opposing constraints, cube out and weigh out.
Okay, break this down for me.
Sure. Cubing out happens when a vehicle reaches its maximum volume capacity before hitting its weight limit. So think of a truck loaded with foam pillows.
Okay, yeah. The trailer is completely full, physically packed to the ceiling, but it's super light. It's well under the legal weight limit.
Exactly. Weighing out is the exact opposite.
Right.
You hit the legal weight limit of the trailer, but you still have like 50% of the physical volume completely empty.
Like hauling a truck full of lead-acid batteries.
Right. So a pure DFL strategy requires designers to manipulate the product's density or its packaging to find that sweet spot where the shipment simultaneously cubes out and weighs out.
I mean, IKEA basically built their entire global empire on this exact concept, right?
Oh, they're the gold standard for DFL.
Because they don't just design a bookshelf and then figure out how to cram it in a box. They design the bookshelf specifically so that it can become a flat carton. The dimensions are reverse engineered from the shipping pallet itself.
Right. By shipping unassembled parts, they drastically increase pallet density, it lowers warehouse holding costs, slashes ocean freight, and it makes it infinitely easier for the customer to get it home. They've essentially outsourced the final stage of manufacturing to you, the consumer.
Which is brilliant. And it's not just furniture. Think about those standard plastic garbage pails at the hardware store. They always have that slight taper to them.
Ah, yes. Nesting.
Right. That taper isn't an aesthetic choice. It lets them nest inside one another.
Right.
Without it, a pallet might hold 20 pails. With the taper, it holds 200. The logistics completely dictate the physical shape of the object.
And that leads perfectly into our next layer. Because if DFL optimizes the box itself, we still have to figure out how to optimize the individual parts inside the box. And we want to do that without reinventing the wheel every single time.
Right, which brings us to standardization and modularization. But I actually have a critical question here. I want to push back on this.
Go for it.
If we standardize everything, don't we lose creativity? Like if every company uses the same generic parts, don't we end up making really boring products and losing that premium feel?
What's fascinating here is that you're hitting on a very real tension in the industry. It's the trade-off between integral design and modular design.
Integral versus modular, okay.
Yeah, so integral design uses custom, highly bespoke parts. Apple is famous for this. Everything inside an iPhone is machined to fit exactly into that specific casing. It gives you incredible premium fit and finish, but, and this is a big but it's incredibly expensive to manufacture.
And really hard to repair, I bet.
Extremely. Standardization and modularization take the opposite route. Modular design uses interchangeable parts. Think about a PC. The RAM, the hard drives, they're standardized modules you can swap between dozens of different brands.
Okay, so you might sacrifice a tiny bit of that sleek aesthetic, but you save massive amounts of money and time.
Massive amounts. And it cascades down to component commonality. This is using a single part, like one universal screw size, for the entire assembly.
So workers aren't constantly switching tools on the line.
Exactly. And purchasing can buy that one screw in huge bulk for a major discount. There's also universality, which is designing one product for multiple markets, like a laptop power supply that accepts both 110-volt and 220-volt power.
Oh, that's smart. You don't have to guess how many US versus European chargers to make.
Right. And to give you an idea of the financial impact, when Hewlett-Packard and Compaq merged, they found out they were making 12 distinct, completely incompatible types of server rack kits.
Wait, a server rack? Isn't that basically just a metal frame?
Literally just a metal frame.
Yeah.
The customer doesn't care about proprietary metal brackets. So HP standardized it. They reduced those 12 incompatible kits down to just 5 universal designs.
Wow.
That single simplification saved them an estimated $32 million over the product's lifetime.
$32 million just from standardizing metal brackets.
Yeah.
But, okay, let's say we have standard parts in flat boxes. If the product still takes a literal genius to assemble or repair, the supply chain is still bleeding money, right?
Absolutely. Which means we need simplification.
Yes, and the formal term for this is Design for Manufacture and Assembly, or DFMA.
DFMA. What does that actually look like in practice?
It's all about mistake proofing. Reducing the number of parts, avoiding super tight tolerances, and making the assembly process visually obvious.
So what does this all mean? It's like writing a recipe where it is physically impossible to add the eggs at the wrong time.
That is a brilliant analogy, yes. You are engineering the human error out of the equation. If a worker has to guess which way a bracket goes, eventually they guess wrong, and you get a defect. DFMA designs the bracket so it physically cannot sit flush unless it's facing the right way.
Oh, the sources actually had a really cool example of this with a US-based pinball machine manufacturer.
Yes, I love this example.
Because pinball machines are so incredibly complex, right? Just miles of wiring, sensors, flippers, all crammed under the board.
It's a rat's nest of parts.
Exactly.
Yeah.
And this manufacturer used DFMA to create an internal assembly harness that can literally rotate 360 degrees, which is huge for troubleshooting. A technician doesn't have to blindly reach behind panels or dismantle the whole machine. They just flip the harness and have instant access to all the wiring.
Fast repair. And that efficiency is what keeps them competitive against lower-cost overseas labor.
And that highlights another concept, design for service. Simplification applies after the sale, too. Making maintenance easy, like HVAC units with easily swapped air filters, it lowers the total cost of ownership. And that drives immense customer loyalty.
Okay, so efficiency and simplicity are great for the company. But let's be real, modern customers demand high quality, they want personalization, and they demand eco-friendly, sustainable practices. How on earth does design satisfy all those competing demands at the same time?
It's a juggling act, for sure. To manage quality and customer desires, the industry uses quality function deployment, or QFD.
QFD, that sounds very technical.
It is. It's essentially a matrix called the House of Quality. It translates the voice of the customer directly into technical specifications. It balances conflicting desires.
Can you give me an example of a conflicting desire?
Sure. Let's say car buyers want a vehicle that feels heavy and sturdy for safety, but they also demand high gas mileage.
Oh, right. Those totally contradict each other. Heavy cars burn more gas.
Exactly. So the House of Quality maps these requirements mathematically. It forces the engineers and marketing team to find the exact point of compromise between steel thickness and aerodynamics before they ever build a prototype.
Okay, that makes sense for quality. But what about customization? If I want a localized product, how do you offer that without losing all the money you saved from standardization?
If we connect this to the bigger picture, the answer is a strategy called postponement.
Postpone, like delaying something.
Yes, delayed differentiation. Instead of building a custom product from scratch, you build generic modules and wait to assemble them until the demand is actually certain.
Ah, the HP printer example from the sources.
Yes. Historically, HP built fully assembled printers for different countries. A French printer, a German printer. But if French demand dropped, they were stuck with useless inventory, because you can't easily turn a French printer into a German one.
So they shifted to postponement. They stopped shipping fully assembled global units, and instead they sent generic base model modules to regional distributors.
Right. And when an actual order came in from Germany, the regional center would drop the German localization kit, like the right manual and power cord, into the box right before it shipped.
That is so smart. And it ties into globalization, right? Adapting a global architecture for local tastes, like how McDonald's has a globally standardized logistics network, but they adapt with vegetarian menus in India.
Precisely. And sometimes those localized constraints lead to massive breakthroughs. That's called reverse innovation.
Oh, right. General Electric is the classic example here.
Yeah, GE disrupted itself. They realized their massive, expensive ultrasound machines wouldn't work in rural clinics in India and China. The budgets and infrastructure just weren't there.
So they engineered a highly portable, low-cost, battery-operated ultrasound specifically for those rural markets.
And here is the reverse part. That low-cost portable machine was so good, it ended up creating a brand new market back in wealthy, developed nations. Emergency rooms and first responders in the U.S. started buying them up.
Wow. Okay, we have to talk about the final big constraint, because the modern supply chain absolutely must be green. Sustainability is huge.
It is unavoidable now. And the framework here is Design for the Environment, or DFE. It means designing for reverse logistics, proactively engineering a product so it can be easily returned, recycled, or remanufactured at the end of its life.
Remanufacturing, that's what Caterpillar is doing, right, with their heavy machinery?
Yes, Caterpillar's remanufacturing division is incredible. If customer needs a replacement engine, Caterpillar sells them a remanufactured one for half the price. But there's a catch.
Right, they only get that cheap price if they trade in their old broken engine block.
Exactly. It's a core charge. The customer gets cheap parts, and Caterpillar gets to reclaim the heavy steel core. They bypass the most expensive, carbon-heavy part of manufacturing, the initial steel casting. They turn returned waste into a highly profitable new asset.
It's a completely closed loop. It really pulls the curtain back on this whole topic.
It really does.
Like, design is not just about how a product looks. It is the invisible machinery that dictates how a thing is built, how it's shipped, repaired, and even recycled. So to you listening, next time you buy flat pack furniture or a customized tech gadget, you will actually be able to see the massive logistical chess game hiding inside that design.
And this raises an important question to leave you with. If companies like Caterpillar are successfully turning old, returned products into profitable new assets, it makes you wonder about the future of ownership.
Oh, wow. What do you mean?
Will we eventually see a world where consumers never actually own physical products, but merely lease the highly engineered raw materials from the supply chain on a continuous, perfectly sustainable loop?
That is a wild, fascinating thought to mull over. Just leasing the raw materials. I love that. Well, thank you all so much for joining us on this deep dive. Keep exploring the hidden systems around you, and we will catch you on the next deep dive.